Okay, so let's just do the second hour. So maybe from some of the questions I had during the break, I just want to clarify what we just did. I wanted to show you a clean reasoning that you can always fall back on in all possible cases in order to know that you found a unique solution to Laplace's equation. Okay? I don't foresee that in the exam I will ask you for a very formal reasoning based on these things. Okay? This is really not the point. This is not a mathematics class. This is an electrodynamics class. I want you to be able to know the physics. I want you to be able to solve these equations, visualize the solutions in many, many different circumstances. But sometimes in life, you gotta do things right. Okay? And that means don't piss around the pot. If you can make a very economical, precise, mathematical statement that serves your purposes, do that. Don't try to be friendly and say, oh, but if you do this, you get that, and if you do this, you get that, and then there's this, and then there's that. Oh, yeah, but you should know, but this is like a very exceptional thing. No. Okay? Keep it simple, and you're trained to do that. Electrodynamics, I think, is a really, really fantastic example of a kind of converged physical theory where these reasonings have been sculpted and improved and polished, so for a century and a half. And there's a very good reason why some formulations are more powerful than others. And very often it's because they get to the point. Okay? And that's what I wanted to show you with this particular thing. Okay? So now, I didn't tell you under what circumstances you'd get one or the other. Now you have new keywords in your arsenal, like Dirichlet and Neumann. You can go read the biographies of those people, very interesting. But for example, how do you translate that to a physical situation? Okay, let me consider two conductors floating in space. Okay? And I tell you these things, they're at a certain voltage. Okay, and I tell you they're conductors at a certain voltage. Well, fine, you know that the conductor is an equipotential. Okay? Therefore, you know the value of the potential at the boundary defined by the surface of this conductor. Okay? Dirichlet. You got another conductor, Dirichlet as well. And I ask you, what's the solution of Poisson's equation? You say unique. Okay? Because I remember J.S. told me that it's either Dirichlet or Neumann, and then it's unique. Yeah? And it's as simple as that. If I give you another problem where instead of having a conductor, which is an equipotential, I tell you, no, I have essentially a surface charge pasted onto a certain surface. And you remember the equation that we saw last time, right? That the derivative of the potential to the normal coordinate was equal to minus sigma over epsilon 0, where sigma is the surface charge. Neumann. Okay? So if I give you the surface charge on a surface, I'm giving you the Neumann condition on this boundary. Therefore, you know that that's enough to get a unique solution of your Poisson equation. Okay? So that's the idea. Okay? But once again, I wanted to give you this because it's a beautiful reasoning, because I think it's the kind of most appropriate reasoning. Sorry, I'm just like waving because there's stuff floating around my eyes, just not because I'm going crazy. So it's just the most beautiful way of thinking about it. Okay, and that's it. So I understand many of you find it a little bit mathematical and stuff, but there is physics behind it, yeah? And it's just expressed through the mathematics. Okay? Any questions about this? Yeah? Because now we're moving to like method of images and separation of variables, which are the next things I want to do. But then I will refer to our discussion about these things as we go along. Okay? Fine. Okay, so let's just carry on. Maybe I'll use a new sheet here. Electronic paper, pretty cheap. Okay, so let's just now go to actual problems where the reasoning we just had will actually give us a little bit of confidence of what we're doing. We're now starting to discuss like tricks and methods to actually compute the potential or the field for that matter. The first one is really like more a trick than a method. Okay, so the method of images. And I presume that you have all played with the method of images in the past. Am I correct? Is anybody unfamiliar with the method of images? Okay, very good. So then we do it. Okay, so, but those of you who are familiar with the method of images, maybe we'll think about it ever so slightly differently after this. Okay. So let's consider a very simple problem. And this simple problem is a problem of two-point charges. And what we're going to do is put, we're going to put charge Q at, let me use the same notations. Yeah, it's a bit confusing notation. At D along the Z direction, minus Q at minus D Z hat. Okay, so really literally, right? I have Q here, I have minus Q here. Okay, and this distance is just D. And that's the origin. Okay, well, we can immediately write down the potential xyz because we know Coulomb's law and how to integrate this thing. So what is this? It's just 1 over 4 pi epsilon 0. You see now my position in space is xyz, but the position of the charge is just along the z direction, so I have to be a little bit careful how I write my distances. What is it? I just have the x squared plus y squared, okay? Plus now, you see, if I'm here, what I need to do is just do the z coordinate minus d squared. And now this whole thing in a square root. And now I have charge minus q, but at minus z. So it's the same thing, x squared plus y squared, plus now z plus d squared. And now I will write the square root like this, because it fits better. Oh, that's not good. Okay. Parenthesis here around everything. Observation. Okay. V is equal to 0 for Z is equal to 0 and any xy. Okay? So, at the midway point between my two charges, the plane perpendicular to the link is an equipotential at V is equal to 0. Okay? So this is just like having a conductor, so an you know, so therefore an equivalent problem in the half space for, well, not is but in. So an equivalent problem in the half space z greater than 0 is that I have charge q at dz hat, and I have a grounded conductor at z is equal to 0 and under. Right? So now I just have my z is equal to 0 plane, and I tell you it's like semi-infinite conductor in there. So the surface at z is equal to 0 is just this equipotential. Okay? There is no way you can distinguish between these two problems in electrostatics. You have to go to electrodynamics to see the difference between these. Okay? Why? Because in the chopped up space corresponding to the half space above the conductor, then it's the vacuum. We have a solution of the Laplace equation. We have the point charge at z that defines, if you want, the value of the field around there. The value of the potential on the conductor is given because I tell you it's a grounded conductor. V is equal to 0. Therefore, the two solutions coincide for the potential. So all exactly the same. Alternately, I could do it the other way around. I could tell you, no, there's a charge minus q at minus d along the z direction. There's a grounded conductor, okay, from z is equal to 0 upwards. And now the solution inside the half, lower half space, z less than 0, is the same as the original one. Okay? So that's the logic of the method of images. If I give you a problem where I have a grounded conductor on the plane like this, with a charge here above it, then this problem is equivalent to a problem with 2-point charges, which is simpler, at least in the half space outside of the boundary condition of the boundary surface of the conductor. Okay? You're familiar with this example, right? Yay? Yay. Now, so what happens, you remember, is that although the value of the potential on the conductor is given, the conductor, because of the presence of the charge at charge q at z, will have an induced charge. So the surface of the conductor will become charged. Okay? And then essentially if you have charge q, the total charge that will be induced here will be minus q. And then at the other end, at infinity in the conductor, there would be a charge positive q coming there because your conductor would conserve charge in total. Okay? So, on the conductor, there's an induced charge. And the way, so how to calculate this? Well, we did this last time because you remember at the end of the last session, somewhere here, we had this equation here. Okay, so the surface charge is related to the the cusp in the potential around this. Okay, so essentially the only thing I need to do, this was equation 271, by the way. Yeah, I think. Actually, did I write what the... Yeah, I mean this one here, right? So sigma is just minus epsilon 0 with now the normal gradient of the potential here. Okay, so sigma of x, y is equal to minus epsilon 0 dv dz at z is equal to 0. And that you can just calculate minus qd with now the distances 2 by x squared plus y squared plus d squared to the 3/2. Okay, so it's just, you know, if you're just immediately under the charge, then the induced charge is like maximally negative, and then it falls back as you go to infinity. Okay, you can do a check. You can check that the total induced charge so you just need to integrate this in two-dimensional space. You can do it in the just planar coordinates. Integral 0 to 2 pi d phi. Integral to 0 to infinity r dr of this this thing minus qd over r squared plus d squared to the 3/2 with a factor 2 pi 1 over 2 pi. Okay, so the integral is done for you in the notes. It's very simple. It's just you just get straight the qd divided by r squared plus d squared square root, and you evaluate this from 0 to infinity, and this is just minus q. Okay, so the total induced charge on the surface is just the converse of the other point charge that you had. So everything is fine. Yes? dr times r. So it's just the Jacobian for the planar coordinates. So r dr d phi. Okay, so that's yes, question?
See the formula with sigma up there, what happened to the epsilon 0 on the right side?
So there's an epsilon 0 here, and from the v itself, there's a 1 over epsilon 0. So these are conveniently like annihilating each other. No more epsilon zeros. Okay. Okay, so that's the idea here. Actually, yeah, I mean, in the notes I give you the force because of course that's what happens, right? So you have your conductor, you have your charge Q here, but because of the induced charge being of a different sign, there is actually a force pulling on your charge from the conductor. If your conductor is this massive thing, then there is actually a physical force on your charge on this. And this is just like the force that you would get from the other point charge at minus d in that direction. Now, the other thing I do is I give you also the energy of this. So you just integrate the field square. Now, of course, the energy of the half problem is half the energy of the full problem. Okay, just because you integrate only over half the space for the very, very same field. So it's that. Okay, so somehow the conductor hasn't put energy in there. Okay, so I mean that's the kind of statement of the method of images. In the notes, I give you the kind of setup for two unequal charges. It's just a game. Actually, the number of games you can play with the method of images is really like absolutely infinite. You'll get a problem or a couple of problems with images here. Doesn't have to be with point charges. It can be with charge distributions. Doesn't have to be with planes. It can be in different coordinate systems. You see, you can immediately play a more nasty game here because I could give you other equipotential surfaces in this problem. I say, no, let me define the surface where the potential is equal to, 1. Yeah, that would be above the plane. And this defines for you a kind of a surface, two-dimensional surface in three-dimensional space. And then, again, I can play an image problem here. I give you the point charge and this very, very strangely shaped conductor. And I tell you that this one I hold at potential 1. And then you would get exactly the same solution as this one. So even in this formulation here, there are already an infinite number of problems that have the same solution because they have the same like sliced boundary conditions everywhere. So the point of the method of images is that essentially that's it. It's a simple trick, But why are we confident that it works? Because what is, in the end, the method of images? It's essentially putting some imaginary boundaries in one problem to create another problem. Okay? But we know that if we just like choose the boundaries to correspond to things that are already fit with our original solution, then it's fine, because it's not like we're inducing a new solution or anything. It's the same problem in the end. So when you use the method of images, you can try to do that. You can try to find a simple charge distribution that would actually fit maybe the boundary conditions you have. So it could be that at some point you're given a complicated problem with boundary conditions. But then you have to be able to see, oh, but that boundary condition would be created by this other little simple charge distribution here. So then I will write my potential from that thing using the method of images. But you'll see, you'll get a couple of exercises on this, okay? And we'll see how it goes. So, Verstappen tempo for method of images. Are there any questions about it? Any interrogations about the method of images? Quite, simple really, but yeah. No? Okay. Then if not, we will consider the method of images as having been mastered by all of you. And we will move on to a much richer discussion about separation of variables. Okay, so let me start on that today. So, okay, so the method of images, called a method, but it's like more a trick. Separation of variables is really something more powerful, if you want. But we'll treat a few cases of this. Now, the idea of separation of variables is that you kind of put some input into your problem using your nose by thinking about what are the dependencies of the function that you're looking for. And your function you're looking for is really the potential. Okay? So the best way is to work out an example. And what we will do is actually do the one that's in the notes that comes from Griffiths. It's a classic example. So just example in Cartesian coordinates to start with. What we have are two infinite grounded conductors in the xz plane at y is equal to 0 and y is equal to a. Okay? And what we're looking for is the solution of the Laplace equation in the space between the plates. So look for a solution of Laplace between the plates. Okay, so first observation, the solution has no z dependence simply by translation invariant. Come in z. Okay? So the Laplace equation simply becomes that the second derivative of our v with respect to x is like this. Okay. Laplace becomes, it's getting like more illegible as time goes by, no? So like a challenge for you to keep up. Sorry. Laplace equation becomes a two-dimensional equation. Okay, just in the xy coordinates, because there is no z dependence. Therefore, the derivative in z is 0. Therefore, I can just toss it out. But v, if you want, in principle, it's a function of x, y, and z, but there's no z dependence. Question?
Why is there x dependence? Because I thought there are two planes that are infinite in x and z directions, and they just have a distance.
X, z, y. So x, x, z, y. So if you want, what we'll be able to, maybe I'm just like choosing one of the directions. It's because I forgot to give you a boundary condition. That's why. That's right. Yeah. Thank you. And the end at x is equal to 0 is closed off with a strip at potential v0 of y. Okay, sorry about that. So it's xz, but we've broken the translational invariance in x by putting a boundary in x. And this boundary condition depends on y. Yeah, so I have like it's as if I had like a semi-infinite slot, like this. So I have no z dependence, because the only dependence I have is this v0 and then like this. Yeah. So now you see, I fulfill the conditions that George Green gave me, because I have all the surfaces, and the other at infinity I don't care about. Okay. So so we have this, and now our boundary conditions are that v of any x at y is equal to 0 is equal to 0. And yeah, there's an equal sign there. We also have that v at x, but y is equal to a, that's also equal to 0. We have now our Dirichlet condition on x is equal to 0. That has to be equal to this kind of source thing that I give you, v0 of y. So this is really just a given thing. And then, so of course, so v, as I take x to infinity for any y, this will go to 0. Okay. So I'm just giving you Dirichlet conditions on all the boundary. Question? I'm only interested in the space y between 0 and a, because I want the solution in y between the plates. I'm not telling you what there is outside the plates. I mean, in fact, the way the problem is set up, it's kind of a conductor at y is 0 or y is a. So you're completely screened from what happens outside. You don't know it. So this, you see, it's a different problem. But now we're looking at inside the space between the plates. That's it. So I don't need to give conditions outside. I don't need to give conditions outside because I've already, if you want, given you the conditions on the whole surface of the volume defined between the two plates. So, so then inside that thing, I have everything I need. If you told me that there was absolutely nothing outside, no other charge distributions and stuff, then I could also use these boundary conditions to solve the other electrostatic problem outside. Okay, but the two are independent. But they're defined by the same boundary conditions. Okay, we'll give you just solutions of a different shape. Okay? Right, so that's it. So now comes the kind of trick for it. You see, we know that if we manage to find a solution, then it will be unique. Okay? So whatever trick or black magic you use to lead me to a solution, I will be happy. Because once you give me a solution, I can verify that it satisfies Laplace in the bulk and it satisfies the boundary conditions you gave me, I know you're done. Okay? So the method of separation of variables makes an assumption as to the form of the solution. And this assumption is very simple. We're going to assume that the solution takes the form that v of x and y is equal to some function big X of x times some other function big Y of y. Okay? It doesn't have to be like that. I'm just saying let's assume it does. Then what I can do is substitute this in Laplace and divide by v to get the following equation. 1 over big X, second derivative of big X of function of little x dx squared, plus 1 over big Y, and let me write the arguments here, big X of x, big Y of y, d2y of y dy2 is equal to 0. Okay? I should have asked this before, but how many of you have not done the method of separation of variables in either a mathematics course, an electrodynamics course, or a whatever course? Sculpting, literature, whatever. Has everybody done separation of variables? So this is obvious to you, okay? Because you see now, it's a great trick. We can just factorize our problem, if you want, in two one-dimensional problems. Because this piece here only depends on x. This piece here only depends on y. Therefore, I can look for solutions obeying that this is going to be some constant and this is going to be minus the same constant. Okay? So for that definiteness, what we do is we take the second derivative of big X with respect to x squared, and we say, okay, fine, this is going to be, just for convenience, it's going to be some k squared times the big X. Okay? And to follow the notes, I'm going to give it a little number here because it's going to be a linear equation, therefore we can combine them. Now we do d2y dy squared, and we'll give it yn as well. It's minus kn squared y. Okay, you see that's the kind of trick here. It's quite simple really because you just get a very simple second order equation. It's either an exponential or an oscillating wave, okay? And the only thing that's important is that if I'm going to combine solutions together, I need to combine the xn and the yn solutions together so that their coefficients cancel. Okay, so most general solution is going to be that our big X function with index n of x, this is going to be the one with the exponential part, e to the knx, plus b e to the minus knx, okay? And the yn function of y is just going to be the sine and cosine, or c sine knx plus d cos knx. Because it's
next to y.
Yeah, not why, but why. I get your point. Why? Thank you very much. 2 less typos. Okay? So, I mean, you see, the whole logic is quite straightforward from here on. You just need to solve the boundary conditions. You just need to solve the. You just need to choose your coefficients, A, B, C, D, so that you actually solve the boundary conditions. Yeah. So I mean, I don't know if I really need to do this. So it's all done in the notes anyway in excruciating detail. It's just a question of like plugging it. So if you look at the first equation that we have, v at y is equal to 0 is equal to 0. So these this thing has to add up to 0. A is equal to 0. D is equal to 0. And so maybe I'll just so from now on, just satisfy the boundary conditions. And see notes. Okay, so yeah, so one thing which is needed is the orthonormality condition. So you just have to know that integral from 0 to infinity dy of, say, sine of pi n y over a with sine pi n prime y over a, that this thing is a over 2 Kronecker delta of n and n prime. Okay, but again, I mean, these are just orthogonal functions. You just need to do things, and then you can compute the coefficient. So, please look at the notes for the actual example, but this is really a completely straightforward thing. Let's see. I mean, this was a simple case in Cartesian coordinates. There's another one also in the notes that you can look at. Yeah, essentially the orthogonality, completeness, relations, and things. I mean, I think this is all very clear from the notes, so we can do this. So what I'd just like to do at the end, I mean, there are a few more examples. So yeah, so see notes for details of this. And now, one comment is that of course separation of variables it can work in any coordinate system, which displays the symmetry of your problem. The only difficulty is that you sometimes have to write down complicated functions. So for example, if you have a spherically symmetric system, you need to play with the spherical coordinates, and the Laplacian in spherical coordinates is one, nasty little piece of work. But yeah, 1 over r squared, partial derivative, partial. Yeah, you take the derivative with respect to r of r squared dv dr, and then you have the plus 1 over r squared sine theta, partial with respect to theta of the sine theta dv d theta. You don't have to know this by heart, yeah, although it's kind of handy. 1 over r squared sine squared theta d2v d phi squared is equal to 0. Fine. So, depending on your thing, maybe your problem doesn't have any azimuthal dependency. So then you can drop the last term. Maybe it doesn't have a dependency like this. Maybe it's really like spherically symmetric, in which case you drop these two terms and you only end up with this. Depending on the cases, you need to make use of this. For the spherical coordinates case, you need to work with complicated things. You need to work with orthogonal polynomials like the Legendre polynomials, but these are the same tricks that you've done in quantum mechanics. Have you done that already in quantum mechanics? Wave functions with Legendre? Okay. So so it's the same kind of logic here. So if you want, these are things that you should be able to do. Okay, so that's the idea of the separation of variables. You know it. Now, next week, I will give you a video course on the multipole expansion. I will make sure that this video is put online. I'll have to do it before Sunday morning or something. So it's going to be there for you to look at. I will be in touch, by email if needed. The exercise session goes ahead. The assistants are there. But, I won't see you next Tuesday, but you'll hear the video if you want. Okay? Thank you.